Before we can understand Gauss's law, we need to understand the concept it's built on: electric flux. Think of rain falling straight down. If you hold a window screen flat horizontally, the maximum amount of rain passes through. Now tilt the screen. Less rain gets through. Turn it completely vertical and no rain passes through at all. Electric flux works the exact same way, but instead of rain, it's electric field lines passing through a surface. Let's put numbers on this. For a uniform electric field passing through a flat surface, the electric flux equals E times a times cosine of theta, where theta is the angle between the electric field and the normal vector to the surface. The normal vector just means a vector pointing straight out of the surface, perpendicular to it. Let's check the three important cases. When theta is 0, the field is perfectly perpendicular to the surface. Cosine of 0 is 1, so you get maximum flux. Phi equals EA when theta is 90 degrees, the field is parallel to the surface, sliding along it. Cosine of 90 is 0, so flux is 0. Nothing passes through. And when theta is somewhere in between, you get a fraction of the maximum. This is the foundation that Gauss's law is built on. One more thing before we move on. In calculus-based physics, we write flux more precisely as an integral. Phi equals the integral of E dot dA. The dA is a tiny area vector with magnitude equal to the area of a small patch, pointing in the normal direction. The dot product automatically gives us the E a cosine theta for each little piece, and the integral adds them all up over the entire surface. That's flux. Let's use it. Now for the main event, Gauss's law itself. Gauss's law says, the total electric flux through any closed surface equals the net charge enclosed by that surface, divided by epsilon naught. Epsilon naught is the permittivity of free space, about 8.85 times 10 to the negative 12. It's just a constant that shows up everywhere in electrostatics. That circle on the integral sign means the surface must be closed. A closed surface has no edges, no holes. Think of a balloon, a box, or a sphere. Not a flat sheet, not an open bowl. It has to completely surround a volume of space. Here's why this law is so powerful. Place a positive charge inside a closed surface. The field lines radiate outward from the charge, and every single one of them pierces through the surface going out. That means positive net flux. The amount of flux is exactly Q over epsilon naught. It doesn't matter what shape the surface is. It doesn't matter how big it is. As long as the charge is inside, the total flux is the same. Now here's the critical insight. What if the charge is outside the surface? The field lines enter the surface on one side, but they must also exit on the other side. For every field line going in, there's one going out. The flux in and flux out cancel perfectly. Net flux is 0. This is why Gauss's law says Q enclosed, not Q total. Charges outside contribute nothing to the net flux. What about multiple charges? You just add up whatever is inside. If you have plus 3Q and minus Q inside the surface, the enclosed charge is plus 2Q any charges outside. Ignore them completely. This is the entire idea of Gauss's law. Total flux through a closed surface only depends on the net charge inside. Gauss's law is always true, but it's only useful for calculating E if you pick the right surface. Here's the problem. The integral of E dot dA looks simple, but in general E could be different at every point on the surface and pointing in every direction. That integral would be impossible. The trick is to pick a surface where E is constant everywhere on it and either perfectly perpendicular to the surface or perfectly parallel. When E is constant and perpendicular, the integral becomes just E times A. When E is parallel, that part contributes 0. This only works when the charge distribution has symmetry. Surface number 1, the sphere. Use this when the charge has spherical symmetry. That means point charges, uniformly charged spheres, or concentric spherical shells. On a sphere centered at the charge, E points radially outward everywhere, perfectly perpendicular to the surface. And by symmetry, E has the same magnitude at every point. So the integral becomes E times 4 pi r squared. Surface number 2, the cylinder. Use this when you have cylindrical symmetry, like an infinitely long charged wire or a charged cylindrical shell. You wrap a cylinder of radius r and length L around the wire. The electric field points radially outward from the wire, so it's perpendicular to the curved surface and parallel to the flat caps. The caps contribute zero flux. Only the curved surface matters, with area 2 pi rl, so the integral becomes E times 2 pi r. Surface number 3, the pillbox or Gaussian pillbox. Use this for infinite plane symmetry like a large charged sheet or the surface of a conductor. It's a short, flat cylinder straddling the plane. The electric field points straight away from the plane on both sides, perpendicular to the top and bottom caps. The curved side contributes zero because E is parallel to it. Only the two caps matter, each with area A, so the flux is E times A from the top, plus E times A from the bottom, 2EA. Here's your quick reference. Spherical symmetry. Use a sphere, integral gives E times 4 pi r squared. Cylindrical symmetry. Use a cylinder, integral gives E times 2 pi r L. Planar symmetry. Use a pillbox, integral gives 2EA. Memorize these three, and you can solve any Gauss's law problem on the AP exam. Let's put everything together and actually solve problems. Example 1. Find the electric field at distance r from a point charge q. Step 1. Identify the symmetry. A point charge has spherical symmetry. The E field points radially outward and has the same magnitude at any distance r. Step 2. Choose the Gaussian surface. A sphere of radius r centered on the charge. Step 3. Apply Gauss's law. The left side. E is constant on the sphere and perpendicular everywhere, so the integral is E times 4 pi r squared. The right side. The enclosed charge is just q. Set them equal and solve for E. Divide both sides by 4 pi r squared. E equals q over 4 pi epsilon naught r squared. And since k equals 1 over 4 pi epsilon naught, this is just kq over r squared. We just derived Coulomb's law from Gauss's law. Example 2. An infinitely long wire with charge per unit length lambda. Find E at distance r from the wire. The symmetry is cylindrical, so we wrap a cylinder of radius r and length L around the wire. The enclosed charge is lambda times L on the curved surface. E is constant and perpendicular, giving E times 2 pi rl. The flat caps contribute zero because E is parallel to them. So, E times 2 pi rl equals lambda L over epsilon naught. The L cancels. E equals lambda over 2 pi epsilon naught r. Example 3. An infinite plane with surface charge density sigma. Use a pillbox straddling the plane. The enclosed charge is sigma times A, where A is the area of each cap. E goes through both caps, so the flux is 2EA. Set it equal to sigma A over epsilon naught. The cancels. E equals sigma over 2 epsilon naught. Notice this doesn't depend on distance at all. The field from an infinite plane is uniform. Now the hardest problem you'll see on the AP exam. The electric field inside a solid sphere of charge. Here's the setup. You have a solid insulating sphere of radius capital R. Charge Q is spread uniformly throughout its volume. We want the electric field at some point inside, at distance little r from the center, where r is less than r. Draw a spherical Gaussian surface of radius little r inside the sphere. By symmetry, E is radial and constant on this surface. So the left side of Gauss's law is E times 4 pi r squared, same as before. But here's the key difference. The Gaussian surface doesn't enclose all the charge. It only encloses the charge within radius little r. Since the charge is uniformly distributed, the enclosed charge is proportional to the volume enclosed. The volume of the Gaussian sphere is 4/3 pi r cubed. The volume of the whole sphere is 4/3 pi r cubed. So the fraction of charge enclosed is r cubed over r cubed. That means Q enclosed equals Q times R cubed over R cubed. Now set up the equation. E times 4 pi R squared equals Q R cubed over R cubed epsilon naught. Divide both sides by 4 pi R squared. 1 R cancels from R cubed, leaving R to the first power. The result, E equals QR over 4 pi epsilon naught R cubed. This tells us something remarkable. Inside a uniform sphere of charge, the electric field grows linearly with distance from the center. Let's see the complete picture. Inside the sphere, E increases linearly from 0 at the center to a maximum at the surface where R equals R outside the sphere. It behaves exactly like a point charge, falling off as 1 over R squared. At the surface, both expressions give the same value, so the graph is continuous. No jumps, no breaks. One more connection to tie it all together. What happens inside a conductor? In a conductor, charges are free to move. They redistribute until the electric field inside is 0. Gauss's law confirms this. If you draw a Gaussian surface inside the metal, E is 0 everywhere on it, so the flux is 0, which means the enclosed charge must be 0. All the charge sits on the outer surface. This is why Faraday cages work. Let's recap the entire lesson. Electric flux measures how much field passes through a surface. Gauss's law says the total flux through a closed surface equals Q enclosed over epsilon naught. To use it, choose a Gaussian surface that matches the symmetry of your charge distribution. Spheres for point charges, cylinders for wires, pillboxes for planes. Inside a solid sphere, E grows linearly. Outside, it drops as 1 over R squared. And inside a conductor, E is always 0. That's Gauss's law. You're ready for the exam.